you know. Yeah.
That was going to happen in I live on campus.
I should probably give a bonus quiz today just to be ironical, but
We should
give 2 of them. Just kidding. So I'll begin with a word of prayer. Dear Father, we thank you for this day, and I thank you again for this class and your creation that we can study. Help us to understand a little bit more about it today, Lord. In your name I pray, Lord Jesus. Amen. So this is lecture 15 for us, believe it or not. And today I'm aiming to, finish what I have to say about chapter 4 in Griffiths, which is still about electrostatics and matter. And towards the end of the chapter, he talks about a few different issues. One of them is the concept of a crystal. And so I just want to say just a couple words about that. He's got some really cool pictures, but basically a crystal, may be easier to polarize in some directions than others. So in this case, the polarization is not given by just one constant, one susceptibility constant, but rather like a whole tensor. All right, and really matrix, if you like. So let me just go ahead and write it as a matrix. It looks like this. It's basically P, the polarization vector, is equal to the epsilon naught times the susceptibility matrix, which I'll call E sub E, times the electric field vector. And here, X sub E, he does like this. It's and he doesn't have this X. I just made that up, but it's like chi E XX, chi E XY, chi E XZ, chi E YX, chi E YY, chi E YZ, chi E ZX, chi E ZY, chi E ZZ. There you go. This is the susceptibility tensor, which of course we can identify as a 3x3 matrix in this context. So this would account for all of the different ways the crystal could be polarized. Like it would interact with electric fields different ways in different directions, right? If the electric field went one way, it would go one way. Different way would be a different way. The case of a linear dielectric, contrast that to the linear dielectric. What did we say the linear dielectric? How'd that go? Remember? How was the polarization related for the linear dielectric? It was P polarization is epsilon naught chi E, right, times the electric field. So, constant, right? I mean, I guess it could in principle be a scalar function, maybe. But I think, really, for the most part, we're assuming it's a constant. So, in this case, if you think about it, it's kind of like your susceptibility tensor, or matrix, if you will, is just like E times this. So there you go. I'm adding unnecessary and physically unhelpful mathematics to Griffiths right now to feel like I did something today. I hope you appreciate that. But in some sense, more generally, maybe you'd have to if you had this for an interesting crystal, I suppose the problem would be to find the eigenvalues and eigenvectors to it. Those would give you principal directions in which you could polarize the crystal. Assuming that the crystal is such that this is a symmetric thing, then you could be sure it was orthonormally diagonalizable or whatever. But anyway, that's not in Griffiths. He just mentions this momentarily. I think it's an invitation towards deeper material physics, which is not in the book, okay? So, but I think it's good to at least pay respect to the fact that not all matter is a linear dielectric, right? It's more complicated, generally speaking, like this, all right? Okay, so let us talk a couple minutes here about energy in dielectric systems. So I'm going to run through a derivation here. And after this derivation is done, if we still have time, then I'll work out maybe like example 4.7 or 4.8 or something like that, all right? So the energy in dielectric systems, he starts by pointing out that as a motivational comment, he begins by reminding us that the work to charge a capacitor is given by what? You may remember this from before, 1/2 CV squared. I mean, I haven't done that this semester, but certainly I have derived that in my 232 course whenever I teach it, right? This is the energy stored in the capacitor, right? And Griffiths points out that if we were to take the capacitor and swap out, so if you had like, if you had an air-filled or if you like vacuum based capacitor, and you fill the gap with permittivity epsilon R material, dielectric, right? Then your capacitance would then be basically epsilon R times the vacuum capacitance, if you will. So maybe that suggests that the energy stored in a dielectric, well, anyway, I don't think. All right, I guess. Well. Goodness, I'm trying to remember how to explain that right quick. I guess if we think about a parallel plate capacitor, you guys can help me out, right? You guys know about those, yes? So if we have a parallel plate capacitor, right? So the thickness D, the area A, and what was the deal? The voltage dropped between the plates is equal to, what was it, D times the electric field between the plates, if I remember right. But the electric field between the plates is also given by, what was it, sigma over what? Epsilon naught. I think that's right because, I think that's right. So sigma over epsilon naught. And, but what is the charge on the plate? It's like, yeah, A sigma divided by A epsilon naught. So that's Q, D over A epsilon naught. And so let's see here. Q, is it Q over V? You guys help me out. I don't remember. This is one of my weaknesses. The capacitance, is it Q over V?
Yes.
Okay. 50-50. It's either Q over V or V over Q. Q over V? Okay, cool. Then this would be A epsilon naught over D, right? And that's equal to the capacitance of the parallel plate capacitor. Right? The area times the permittivity between the plates divided by the distance. That's the formula for the parallel plate capacitor, right? And so it's fairly evident that if you swapped out the material in between the plates for an epsilon sub r material instead of epsilon sub naught, you just multiply, right, the C. So like C is a epsilon Oh, I'm an idiot. I forgot. That epsilon sub r, I forget all this stuff, guys. What's epsilon sub r? It is, rats. Yeah. Epsilon r is equal to epsilon divided by epsilon naught, I think. Or maybe the other way around. Oh, goodness gracious. I don't know if I don't know if I've written that down or not either. I can't remember. It seems right. I'm not sure I wrote this one down. I talked about epsilon, you know, but I don't think I actually talked about the epsilon sub r. I mean, we could figure it out from what I have on the board. Maybe you guys could figure it out. I'm not sure I can at the moment. If that's epsilon, working backwards here. A epsilon naught? Did I do that right? Yeah. Okay, epsilon naught over D. I guess epsilon r must be epsilon divided by epsilon naught then, huh? Because then epsilon naught times epsilon r is equal to epsilon. So this is a epsilon naught over d times epsilon r, and then everything is simpatico. All right, great. Let us stop talking about this stuff. So moving on here, this is the relation between the capacitor with or without the, dielectric material. The epsilon sub r is bigger than 1, all right? Like epsilon is bigger than epsilon naught, corresponding to, like we talked about last time, it lowers the strength of the electric field from a free charge as it would be otherwise, right? Q over 4 pi epsilon r hat over r squared is smaller than Q over 4 pi epsilon naught r hat over r squared, right? So the electric field from a given point charge is the largest it can be in free space. When there's matter in the way, the field is reduced through like this polarized shielding, as Griffiths explains. And, all right, so he's like, recall that remember what the energy stored in an electrostatic system was?
One half E squared over epsilon naught. Well, integrate that over space.
You said it was epsilon naught over 2 integrate E squared, E squared?
Something like that.
D tau over space? Right. Correct. That's the total electrostatic energy for a system. And so he says, we suspect from the dielectric filled capacitor that in the presence of matter, maybe, like what happens? If this is the energy if we replace the vacuum capacitor with the non-vacuum, I should really put a vac up here, If we replace the vacuum with, it doesn't, this could be either one is the thing, but this is independent of the construction of the capacitor, right? This formula. But, well, anyway, let me stop belaboring here. So we have then, as he says, we suspect from the dielectric filled capacitor that this is going to be, we're going to go to the work needed to assemble such a system is epsilon naught over 2 integral of epsilon sub relative E squared d tau. But let's see here, now that I've got all my silly notation in order, we can trade that epsilon So this is what? All right. We're all the way in now. What's epsilon times epsilon naught times epsilon r is epsilon. So we've got an epsilon E vector dot E vector, right? But what is epsilon E? We're in a linear dielectric right now, so epsilon E is just, that's D, that's the electric displacement. So probably we might hope that the work needed to charge a dielectric filled capacitor is given by that, which gives us a kind of expectation of what the energy is stored in a matter. If we have like a material system, we can calculate the electrostatic energy needed to establish such a system by calculating the integral of 1/2 d dot E d tau over the system. Like this is what replaces, in the previous context, like electric fields in a vacuum, we just integrate epsilon naught over 2 E squared, right? In other words, the energy density in the vacuum is epsilon naught E squared over 2. The energy density in a linear dielectric, if you believe this, is apparently 1/2 d dot E. All right, that's the energy density. And so let me show you Griffith's exciting derivation of this, yes. So here it goes. So he says to bring in a bit of free charge at a time, if we bring in just a little bit of free charge density, that takes us a little bit of work that would be given by the integral of that little bit of charge, little change in the free charge density integrated over d tau. So if we integrate the change in the charge density over space, well, the cost to us in terms of the work to increase the density just by a little bit is given by that integral, right? But we also know, you remember this, that the divergence of the electric displacement is the free charge density, right? And so that tells me that the change in the free charge density can also be gotten from the divergence of the change in the displacement. And since that's true, we can look at the little bit of work that's needed to increase the charge density, the free charge density, by this little bit in light of that relation, right? And as such, we'd have so let's put it in here. We have, change in W, integral of what was the change in, well, so we're going to replace this guy with that guy, okay? The divergence of the change in the displacement times V d tau. Now you've seen this kind of thing before. What do we do when we're faced with an integral like this in some kind of, theoretical calculation? We're gonna use the power product rule. So like the divergence, right, of the change in the displacement times the potential is the divergence of the change in the displacement times the potential plus the change in the displacement dot product with the gradient of the potential. So look at that. Look at what you have. We have the divergence of, we're currently with this term right here, right? So we're going to trade it for one of these guys minus one of those guys. So I have the integral of the divergence of the change in the displacement vector times the potential minus the change in the displacement vector dotted with the gradient of the potential. All of this gets integrated over space. Now, can you guys, well, let me write this more conspicuously. Yes, thank you. I had trouble saying magnetic in the previous lecture, so, you know, well, in differential equations today, I was trying to say magnetic, and yeah. So this is plus the integral of del, the change in d dot what? You fill in the blank for me, guys. What is minus the gradient of the potential? Yeah. So if you take my physics 232 and you can't answer this question, it displeases me. But you can pass. And there is a difference between that course and this course. I'll still be displeased. But if you can't answer this on the final, I would have to fail you. Like, this is such a, like, it's not knowing this, I think that's immediate grounds for firing, like, in this course. Like, we can't go on. We can't go on past this point. Like, you have to know this, you know? Sorry. You guys know it, though. So this is actually the electric field, right? And then this we can do, so if we're doing this whole thing over, you know, like some volume, then this, by the divergence theorem, is the integral over the boundary of the volume of del D, right? V dot dA vector, right? Oh, man. Right? But if we're taking this over a very large region, I mean, for this discussion, we're assuming that we have like a localized charge distribution, all right? If the charge distribution isn't localized, then these kinds of things blow up. So it's not really that interesting, right? But if the charge distribution is localized, then certainly we can assume that the voltage, the potential, is taken to be 0 at infinity. And as such, this term is 0. And so, lo and behold, we have found our way. I was about to use the wet eraser. I gotta be careful here. You know? Because if I use the wet eraser right now, then poor Miss Dromby, Professor Dromby, rather, she's gonna have a mess come Monday. Although, do you guys have any peanut butter?
Yes, actually.
You do have some peanut butter.
It happens to be in a sandwich, but that can be solved. If you buy me a sandwich, I'll provide a sandwich.
See, no, this is waste. Like, we have to put the peanut butter there right before she teaches. Otherwise, it doesn't really count. Because I don't want to get somebody else. This is, you know.
And they usually clean it during the year.
Have you seen the deer head in her office?
Oh, yeah.
That's me. Daniel and I went to the dump one day, and we're like, Daniel's like, can we take it home? Because there was a mounted deer head at the dump, just sitting there. And I was like, no, we can't take that home, but we can take it to school. And so naturally, I had to find a way to mount it in Professor Dromby's office. It almost gored her one day. It fell off the wall and fell. But anyway, wouldn't that be a cool obituary? Let's see here. So, sorry, Jacob. I know you would like to have a mother, but in terms of comedic deaths, this is pretty up there. Hopefully that won't happen. Let's see here. Probably should do a better job mounting it, you know. Anyway, so this is a little bit of work that it takes to change in the charge density like that, right? So then So then he also argues for, so I guess I said that this was for a linear dielectric, but actually I have not invoked the linear dielectric assumption anywhere in here. All right? I did over there to motivate things. All right? I mean, that middle board is just to motivate what our current search for a formula. All right? And anyway, so for a linear dielectric, we have that this electric displacement is, epsilon times the electric field. And so if we look at 1/2 the, change in d dot E, right, that's equal to 1/2 the change in epsilon E dot E, which is 1/2 of, so by the product rule, basically, this just becomes epsilon times the change in the electric field dot E which of course is the change in epsilon E dot E, which is the change in the displacement dot E. And then if I take this and go up here, then that gives me 1/2 the integral of d dot E d tau. So at least for a linear dielectric, we have that the energy density is d dot E over 2. So energy per volume E dot D over 2 linear dielectric. I guess this isn't technically true for more exotic materials. Like, I guess you'd actually have to work out that integral that I have on the board there. All right, so we have a little bit of time left. Not a great amount, but enough, I think, time for maybe one example. I'll let you guys pick it. Yep.
Does any of that stuff have primed coordinates?
Primed coordinates. No, I mean, this is the integral. This is the integral over the fields. So yeah, I don't know. Like, that's a good question. I don't know if these things make sense if you have, like, I'm not sure how to interpret them if there's a point charge. I mean, if you try to do the integral, what happens if we try to calculate the energy in the Coulomb field, for example, over all space? How much energy is that? Have we done that in here yet? Maybe it would be good for us to try that on for size. Let's try to work that out. See how that goes. When you get right down to it, I think the considerations of the energy it takes to build a system, these are the arguments I'm most suspicious of in Griffiths. And just generally speaking, the subject matter. Like, how do you, what does it mean to bring an electron in from infinity and build things? Like, you can't actually do that, you know? So what is it precisely we're calculating? I don't know. I'm not saying these formulas don't have meaning. I'm just saying I think some of the questions which are raised, I'm not entirely sure they're meaningful. But then again, what do I know? So that formula right there, the work epsilon naught over 2, the integral of what did we say, E squared d tau, right? let's work that out. What is the energy? What is the energy for the Coulomb field in all space, right? So the Coulomb field is what? Q over 4 pi epsilon naught r hat over r squared, right? So E squared Q squared over 4, 16 pi squared epsilon naught squared, right? 1 over r to the 4th. What's d tau? So let's calculate the energy in the Coulomb field out to radius, let's say, big R. So we got integrate from 0 to 2 pi, integrate from 0 to pi, integrate from 0 to r, r, q squared over 16 pi squared epsilon naught squared 1 over r to the power 4. And what's my d tau? Help me out, guys. It's r squared sine theta d theta, my bad, dr d theta d phi, as I've got it currently written. And so, well, maybe there's hope for us. Maybe I'm thinking of something else. Maybe this is okay, actually. So I got q squared divided by, looks like 32 pi squared epsilon naught. What happens? You get 1 over r squared. That integrates to like minus 1 over r, right? Right? The integral of 1 over r squared is minus 1 over r. So I take that, I got to evaluate that thing from 0 to r. And this jazz over here, we know what that integrates to. 4 pi. We've been down this road before. Integral of sine gives you 2. The integral of d phi gives you 2 pi. 2 times 2 pi, 4 pi. And so if I haven't made a mistake, oh man, this seems like it actually is calculable. That doesn't feel right. Thinking of a line charge? Well, I don't know. But, well, there's a 4 pi here, right? And, oh, oopsie. See, we didn't even need an infinite sphere. You can give me a sphere of radius 0.00001 around the Coulomb field. How much energy is there? Oh, infinitely much. There's like a whole half page in Griffiths trying to talk around this. You can read that page, see what you think of it. But it says what it says, which is that the interpretation of this, well, okay, so something's wrong, obviously, right? We can't have, I mean, should there be, well, I guess that's the question, is there something wrong? Is there an infinite amount of energy in the Coulomb field?
There's an infinite amount of charge.
What happens if instead of, if there's
Charge in the infinite small.
well, that's the thing, is the Coulomb field does, like you say, it puts the charge density as, Q times the, the three-dimensional direct delta of R, right? Indeed, it is low. I mean, this is straight up the finite charge at a mathematical point, right? And you can comfort yourself that this mathematics doesn't make sense because of that. right? I think it's true if instead we did something like rho of r, q divided by 4/3 pi a cubed times, that, okay, for 0 less than or equal to r less than or equal to a, and then 0 for r greater than a, we could work that out, right? I mean, let's do that. What is this? This is probably better than me doing the examples at the end of chapter 4 anyway. Let's do this. All right? Yeah. So I'm going to erase this. I shouldn't erase the top thing because I want to calculate the energy stored in this field. This doesn't have a point-like singularity in it, does it? See what I'm doing? I'm making it has uniform charge density out to radius a, and then it's 0. So what this is a model of is a point charge that has radius a, right? And so you've got, basically that's your point charge, and then that's it. So what's the electric field? Well, you know how the story goes. We have E times 4 pi r squared is equal to Q enclosed divided by epsilon naught. This is for 0 less than or equal to r less than or equal to a. But the Q enclosed is actually, it's Q over 4/3 pi a cubed times 4/3 pi r cubed, right? Because it's a constant density, so the constant density times the volume that's subtended in my current, so like here's the picture of what's going on, guys. Here's the charge, here's my Gaussian sphere inside the charge, okay? Oh man, yowzers! So look, I'm just deriving the usual thing. The 4/3 pi's, they be canceling, and we get, Q r cubed divided by epsilon naught a cubed, right? So my electric field inside the uniformly charged sphere is simply given by Q r cubed divided by 4 pi r squared epsilon naught a cubed, which is actually Q r over 4 pi epsilon naught a cubed, right? That is the field inside the uniformly charged sphere. Now there's no divergence at the origin. That divergent electric field at the origin is what gave us the infinite energy. And then, of course, you know the deal. If we put our Gaussian sphere outside the charge, then what happens? We're back to just Coulomb's law again, right? Then we get E Q over 4 pi epsilon naught, 1 over r squared, right? And these are both, by the spherical symmetry here, radial. So what's the energy stored in this situation? What's the total electrostatic energy of this system? I think he might call it the self-energy. Well, we can calculate the integral of epsilon naught over 2, right? E squared d tau, and what's that go? Well, that goes like epsilon naught over 2, integral from 0 to a, right? Of what? Of Q r squared divided by 4 pi epsilon naught a cubed. And then we know what happens to the rest, right? The rest of it gives us a what? 4 pi. So let's just write that down. And then plus epsilon naught over 2 times 4 pi. Let's get it out there. Integral from a to infinity, right? Of now, we've got ourselves a q over 4 pi epsilon naught. Well, it's the thing I erased here a second ago, but it was 1 over r squared, right? But I think I forgot the square. This is squared, right? I'm missing some squaring, right? This is supposed to be squared, right?
Would you not be?
And this is supposed to be squared. Yeah, what you're saying? So this is actually, this should be what? R to this squares, this formula squared and gives you an r squared, but also the d tau gives us another r squared. This is supposed to be r to the 4th, right? Did you ever tell me?
Yeah.
Excellent.
Well, wouldn't it be r cubed in that case?
But remember, we're integrating e squared, so the r squares.
Oh, right.
So I get an r squared times the r squared and the d tau.
The Q also squares.
Yes. Squares and squares. Squares, not a square to spare. Let's see here. And then, so yeah, we got ourselves a, 4 pi epsilon naught over 2 out front. And then there's another 4 pi that I already got the 4 pi. So the 4 pi that, and then q squared over 4 pi epsilon naught a cubed quantity squared. And then we've got, r to the 5th over 5 evaluated from 0 to a. Now that's not so bad now. And then plus q squared over 4 pi epsilon naught squared. And then we've got, minus 1 over r evaluated from a to infinity. Now the infinity is harmless. And lo and behold, we've got a, q squared divided by, looks like 4 pi epsilon naught. And then I get a, what? I get a to the 5th over what? 5 a to the 6th, did you say? And the 0 gives us 0. And then over here, plus, I think just 1 over a, right? So in other words, 6q squared over, this is 6/5, 1 over a, right? And then, so 5 to 20, if I haven't made a mistake. So we could make that a 3/10. It's that localization of charge at the origin which leads to the infinity and the energy. Like I said, there's like a whole half page of Griffiths where he tries to explain away this embarrassment, as he calls it. I don't know if that's in our part of the book. That may be later. I read the whole book, so I don't remember which part sometimes I'm remembering.
This wouldn't work with the cylinder.
With a cylinder?
Because then it would go down to the power block.
Oh yeah, if we had, that's the thing is, if like you said, if we had a line charge, then we end up with like a log from the, I think we just get, well, I don't know, yeah, if we take infinite charge distributions, we get different kinds of infinities for the energy because of the extent of the distribution. But anyway, I hope I've showed you guys enough for you to finish the homework from chapter 4. What I test on chapter 4 will be based on the things that I've said that are hopefully reasonable earlier this week. And, I think we did this one thing that to find the energy in the linear dielectric, we calculate, the integral of d dot e, sort of the analog of this formula for the linear dielectric is nice to know. There's an example at the end of the chapter where he calculates the work that it takes to push a dielectric into a capacitor. That calculation is very cool because as he explains, the whole thing is based on the fringing fields, which we can't actually calculate the explicit form of, but he has this infinitesimal pushing argument, and he's able to calculate the work that's needed to push the thing in, and he explains basically the explanation. It's all based on the fringing fields, which you don't have formulas for, and yet you can kind of calculate the work it takes to push the linear dielectric into the previously empty capacitor.
Just calculate energy before and after.
The what?
Energy before and after.
I suppose, but you got to be careful because you'd be assuming it's. I mean, maybe is it okay to assume it's conservative? I don't know. But if you look at page 203, well, I'm sorry, I have a printout of the 4th edition, so my page numbers could be wrong, right? You guys probably have a PDF of the 5th edition. Yeah, you're better at this than I am, but
You want one?
yes, please. So, I guess I could just look again. But he explains in terms of a couple different scenarios, one being that you hold the charge on the plates fixed while you push the dielectric on. The other one being that you hold the voltage between the plates fixed as you push the dielectric in. Depending on which you do, one would require energy being input from the voltage source to hold the voltage constant. So one would require a battery doing work, the other one didn't. And he claims his derivation is good for both scenarios all at once. And it's a very cool argument because he doesn't have formulas for the fringing fields, and yet he calculates the work that it takes to push the thing in. It actually, I think it's as he says words. He says, just as a conductor is attracted into an electric field, so too is a dielectric. For essentially the same reason, the bound charge tends to accumulate near the free charge of the opposite sign, but the calculation of forces on dielectrics can be surprisingly tricky. And then he goes on, but that's a cool example. And I don't know, the other two examples I didn't get to cover today. That if I had my druthers, I would have covered examples 4.7 and 4.8, but I can't let perfect be the enemy of good. So good luck finding your cars today amongst the seafarers. See you guys.